In this section, we're going to be looking at binomial probability distributions. So these are a special category of discrete probability distributions that meet four criteria. First is the procedure has to have a fixed number of trials. Second is the trials must be independent of each other. Third, outcomes must belong to one of two relevant categories, kind of like a success, failure, true, false, something like that. And then fourth, the probability of success has to remain the same in all trials. Now, keep in mind that if we apply our 5% rule here, that means that if we have dependent events, but the sample size is no more than 5% of the size of the population, we can still treat them as independent and we could still consider a binomial probability distribution. Also keep in mind that when we're looking at our outcomes, the options have to be specified as two and only two possible outcomes, thus the bi and binomial probability distribution. So these can be a success failure, they can be an acceptable defective, such as the example we looked at when we were looking at baggage scales and deciding whether or not they were whether they worked or they did not work. So anything that has two possible categories, and that is all, okay, and seen as being opposites. So when we're looking at these, some of the notation we need to pay attention to here is N, X, P, and Q. This is covered on your book in page 211. Now N refers to the number of fixed trials that a procedure has. So when we're looking at the procedure as a fixed number of trials, however many of those trials there are, that will be our N. X is going to be the number of successes that we are calculating for. So if we're going to do, say we have 6 trials and we want to know what's the probability of having 3 of them be successful, then our N would be 6 and our X would be 3 because we're looking to have for 3 successful outcomes. P represents the probability of getting a successful outcome in a single trial. Now keep in mind, what P is going to be set for is going to be determined by the solution you're trying to solve for in the problem. So what we set as a success is going to depend upon what we are trying to accomplish or what kind of question we're trying to answer. So P is always connected to X. Q is the probability of the opposite option of failure. Keep in mind that because all possible probabilities sum to 1, the sum of P and Q is equal to 1. And we're going to see this algebraic again in the future as we look at some of these problems. So let's look at specifying first of all whether the following problems produce a probability distribution or not. So be sure to identify how they meet each of these 4 criteria. So pause the video here, take some time and go through problems number 6, 8, and 10 in your book for this section. And then make sure how they address each of these 4 criteria. And then once you've got that in your notes, turn the video back on and let's check them together. Okay, so number 6. We're looking at this one is looking at a number of births. So we have 291 births, so those count as our trials. That's a fixed number. The trials must be independent, so we're assuming there's no dependency between these couples. The outcomes must belong to one of 2 relevant categories, kind of success, failure. Since the method we're looking at here is the Y-sort technique, then birth of a boy is going to count as a success. Now, notice, if we're interested in the X-sort technique, then birth of a girl would be counted as a success. So keep in mind, what we're setting as a success and a failure is dependent upon the goal of the particular problem or process. And then lastly, the probability of success remains the same in all trials. This would also be true for number 6. Now, number 8 is a little bit more complicated here. So first of all, procedure is a fixed number of trials. So we have 1,000 adults, so that's set, and that is going to be our N. The trials must be independent. We would assume that these were independent of each other. These people are not related to each other in any way. Now, the outcomes, in order for this to be binomial, has to be one of 2 relevant categories. Now, notice number 8 has several different categories. So we have potato, corn, broccoli, and tomato. So we have 4, and then others. So we have a total of 5 categories. So if we were processing all 5 of those categories, it would not be a binomial probability distribution. However, notice who's ordering this particular survey. That is the potato commission. So they are probably interested only in whether or not people rate potatoes as their favorite vegetable or not. So if we took that data and we altered it to be potato as favorite vegetable, which we count as success from the commission's perspective, or all of the others counting as not potato, which from their perspective would be a failure, then we could take that data and convert it to a binomial. And lastly, the probability of success, we would have any reason to suspect that these would not be different in different trials. Last, number 10. So here we're looking at selecting 10 senators without replacement and recording the number of terms they've served. So we do have a fixed number of trials here. We've got 10 times. The trials must be independent. Now notice these senators are being selected without replacement. So that means that these are in fact dependent trials. So we also, if we're looking at this one, notice that 10 out of 100 senators, so we're pulling 10 senators out of a total of 100, does not meet our 5% rule. So we cannot assume that even without these are without replacement that we can treat them as independent. We will have to treat them as dependent events. So that means this is not a binomial probability distribution. Notice also that the data is currently being recorded is number of terms served. So that would not be a binomial because it does not have a success failure rate. Now, if we wanted to convert this data to a binomial, and we were willing to talk about it in terms of having served 2 terms or more, then we could count that as a success, i.e. you were reelected, people were pleased with the work you did, so you would have a category of 2 or more terms, which would count as your success, and only 1 term, which would count as failure. So we could reorganize that data to make it a binomial if the trials had been independent. So number 10 is the only one that we really can't convert into being some type of binomial probability distribution. Alright, now we're going to work a little bit with these distributions, solving problem number 13 on page 218. So here, the math portion of the ACT consists of 60 multiple choice questions, each with 5 possible answers, A, B, C, D, and E. Now, assume that you guess the answers to the first 3 problems. We want to find the probability the first 2 guesses are wrong and the third is correct. Now, before we start moving into processing our numbers, we need to clearly label what we are looking at here. So if we were writing this out in a probability formula, we'd have probability of WWC, where W represents a wrong answer and C designates a correct answer. Be very careful to make sure that you're identifying what you're solving for and labeling this as you go throughout the problem. It is not uncommon for students to have done their calculations correctly, but still lose points because they interpret and apply the results back incorrectly to the problem that they were being asked to solve because they were not labeling their information correctly. So don't let that happen to you. Looking at this, and we're going to use our basic probability binomial probability distribution that we have here. P of A equals number of ways A can occur over number of different simple events. So when we're applying this basic probability distribution, this basic probability formula to binomials, what we're going to have is probability of W times probability of W times probability of C. So, if we're looking at our probability of W, the number of ways that a wrong answer can occur is 4. The number of total different possible answers is 5. So for our probability of W is going to be 4 divided by 5. And our probability for correct is going to be 1 divided by 5, since we have only one way of getting it correct. Again, we're assuming these are all independent, so our probability for W, for getting one wrong, is going to be the same for each trial. So we set that up. Here we can see 4 out of 5. And then we get 0.8 times 0.8 times 0.2, which gives our overall probability of the first 2 guesses being wrong and the third being correct is 0.128. Okay, now let's take a look at dealing with a little bit more of a complex probability problem. So whenever you're doing a binomial probability distributions, you're going to want to make a list of all the possible arrangements that you can have. So we're going to use this information in the next step. So here we need to list out all the possible ways that we can have 2 wrong answers and 1 correct answer. So we can have the first 2 correct answers wrong and 1 correct. We can have a correct answer in the middle, or we can have the correct answer first followed by 3 wrong answers. So if we find the probability for each of these possible arrangements, we're going to use exactly the same formula that we used above. So pause the video here and go through and compute this for each of these other 3 possible arrangements. When you've got all your answers worked through, turn the video back on and let's correct them, check them together. So you should have got 4.5 times 1.5 times 4.5 for the first one. And then for the second one that we're looking at, the one in green, 1.5 times 4.5 times 4.5. We do the calculations for that, we're going to see that we in fact get 0.128 for each of these other possible arrangements. So remember, if we looked back at our criteria, we were having to have the same probability for each of these. So when we're looking at all three of these, ordering them together, they all have the same probability of 0.128. So then, based on this information, we need to ask what is the probability of getting exactly one correct answer when three guesses are made on this set of three SAT math problems. And to solve this question and answer, we're going to plug our data into a table that looks like this. So we're going to take the number of ways, a number of arrangements that are possible, and we're going to multiply it by the probability of any one of these number of arrangements, and that is going to give us our answer. So here we're going to plug in 3. Remember, we had 3 possible arrangements that we just went through, and then we're going to multiply it by the probability that we had of any one of these arrangements, which is 0.128. We plug those into this table and run our calculations, and we get 0.384. So this is going to be the probability of getting exactly one correct answer when 3 guesses are made on a set of 3 ACT math problems.